I think we have no more for this term, but then we've got quite a lot of talks coming up in the new year. And as I said already, there's somewhat of a theme of inter-theory relation, classical quantum going on. So hopefully we'll be able to see connections between the talks. So yeah, maybe we'll just start now. So it's a really great pleasure to have Joshua Rosaler come to speak to us in the Bristol kind of philosophy of physics, philosophy of science seminar series. I've known Josh for, I guess, 5 or more years. I saw him give some really fascinating talks over the years, and particularly relating to classical quantum transitions and inter-theory relations. So Josh has studied at many prestigious institutions, including, am I right, Princeton, Columbia, and Oxford? Is that correct?
Harvard.
Ah, almost. Harvard, Columbia, and Oxford. He's now part of the epistemology of the LHC project, which is a really fantastic and fascinating project, and they're based in Aachen. And he's going to talk to us about the straw men of anti-reductionism, a case study in quantum classical relations. Go ahead, Josh.
Thanks so much, Kareem. Yeah, and thank you all for coming. Yeah, I was really excited to give this talk to this audience in particular, because I know just from all of your work that there's, I guess a certain way of looking at questions of inter-theory relations that maybe not everybody in the philosophy of physics shares. But I also hope to be challenged as well. Yeah, so basically what I want to do today is really argue that the kind of general skepticism towards reductionism in philosophy, which I think has been waning to some degree in philosophy of physics in recent years, right, is kind of geared against straw man notions of reduction, right? So notions of reduction that in some sense don't really capture what physicists tend to mean when they talk about reduction between theories in physics. And so what I want to argue is that the concept of reduction really most relevant to reduction within physics is a functional instantiation-based notion. And that anti-reductionist arguments for multiple realization or singular limits, right, yeah, they don't really apply to this notion of reduction. And that for that reason, the kind of a large source of the skepticism has just been sort of misplaced. Okay, and that's to say nothing of philosophy of mind. It's really just talking about relationships between theories and physics for the moment. All right, and what I argue is that that there's still room, of course, for anti-reductionism and for skepticism about reduction, but that skepticism should really be focused elsewhere. It should be focused on particular gaps in the arguments that are invoked to show that reduction occurs in particular cases, right? So it should really focus on the kind of particular, on a case-by-case basis, the particular sorts of functional reduction, the particular arguments that are used to illustrate functional reduction, and particular sorts of gaps in those arguments. And in particular, right, I identify 2 sorts of gaps, deductive gaps and inductive gaps. So this is kind of the general philosophy of science part of the talk. And in the second part of the talk, I really want to go into more philosophy of physics and consider a case study, right? In particular, right, justifying the claim that all classical systems are quantum. And so the goals of this section will be first to kind of serve as a case study for the claims of the first part. But in doing that, I want to outline kind of the main steps of the decoherence-based account of classical behavior and highlight in particular gaps in the functional reduction that can be affected on the basis of the decoherence-based account. So highlight the room for anti-reductionism, right, relative to that account. And then emphasize the role of something called quantum trajectory unravelings, which I think are really important to that story, but have been largely overlooked in philosophy of physics. And in doing that, I'll argue also that formal H-bar goes to 0 limits based on kind of closed system, non-decoherence-based results, right, are largely kind of tangential to questions of functional reduction, right, in large part because of their unrealistic physical assumptions, namely that they don't incorporate the effects of the environment. And so difficulties with those sorts of formal mathematical limits, I think, are really sort of not a threat to reduction in the functional sense. And these results, although they're related right, to kind of decoherence-based accounts, right, they're largely kind of tangential, I would argue. And that rigorous proof of reduction. So one approach to reduction, the kind of highly formal approach, really is to aim at the kind of rigor of a mathematical proof. And I'll argue that that's really too much to hope for, but that compelling mathematical arguments can still be given. Okay, so part one. All right, so just a bit of a refresher. Right, so Nichols, right, in his 1973 paper, distinguishes between two types of reduction, right? Nichols-Schaffner reduction, which he calls reduction one, right? And this basically imposes two requirements on the reduction between theories, right? So this requirement of connectability, right? There should exist bridge laws that express novel features of a high-level theory in terms of a low-level theory, and deducibility. So with the aid of bridge laws, it should be possible to deduce the laws of the high-level theory from those of the low-level theory. And reduction two is a claim that the high-level theory, right, was just using that to indicate the less general theory, the less encompassing theory, but that should in some sense be a formal mathematical limit of the low-level theory. But of course, this is, right, a very kind of schematic, right, equation. It doesn't really have any kind of concrete mathematical meaning as a general requirement. Okay, so the anti-reductionist, so I'll just briefly review kind of arguments against reductionism. So perhaps the most influential kind of source of skepticism about reductionism within the philosophical literature is based on Fodor's arguments for multiple realization. And so Fodor kind of addresses his arguments towards a Nichols-Schaffner-like sort of notion of reduction. And right, he assumes that the bridge laws of Nichols-Schaffner reduction, right, require the identification of each natural kind in the high-level theory with some natural kind in the low-level theory. And so that's that the relationship between natural kinds of the two theories be one-to-one in a sense. And because multiple realization makes that relationship many-to-one, right, it's impossible to associate just a single natural kind of the low-level theory with any given natural kind of the high-level theory, right? So the relationship between natural kinds of the low-level and high-level theory is many-one, and according to Fodor's definition or interpretation of Nichols-Schaffner reduction, right, that which requires that it be one-to-one, right, that the multiple realization blocks reduction. All right, now I guess this depends on how you read Batterman, but I guess I thought that I'd come across some explicit statements to this effect from him. That, right, reduction, right, requires, right, so in cases where some limit is non-singular, right, reduction is blocked, right? So reduction of classical to quantum mechanics is blocked because, right, the h bar goes to zero limit, right, is singular and doesn't commute with the time goes to infinity limit. And so at least my interpretation of Batterman, and although Michael may wish to differ on this, was a rather kind of explicit rejection of reduction and reductionism, and particularly in the case of quantum classical relations, on the basis of the fact that certain singular limits are singular. But certainly maybe that's something we can discuss in the after the talk. So more recently, especially within the context of space-time functionalism, right, there's the notion of functional reduction has become popular. Right, and this is really the sort of notion that I would also advocate in the context, right, of physics more generally. I think it does the best job of capturing what we mean when we talk about one theory in physics reducing to another, right? Because insofar as claims of reduction typically take the form all theory A systems are also theory B systems, right? To speak loosely, right? So all classical systems are quantum. So that mode of speaking, right? So the notion of reduction reflected in that manner of speaking, right, I think is best captured by functional reduction, and yeah, so of all concepts of reduction, I think it's really the functional approach that best reflects this usage. Right.
Sorry, do you mind?
Yeah.
Do you mind us asking explanatory?
No, not at all. Not at all. Yeah.
I was just going to say, like, is it important that it's asymmetric, that relation?
Yes.
Okay.
Yeah. So it can be many to one. So yeah. So I'll go into that in a bit. Yeah, so it's not the case that all theory B systems are also theory A systems, right? Right. So when people, when we say that all classical systems are quantum, right, we don't generally also mean to say that all quantum systems are classical, right? The claim is one that is that one theory is strictly more universal, more empirically encompassing than another. And okay, so right, so what's needed to show that all classical systems are quantum, right? So how do we translate that sort of loose intuition into mathematics? And well, I'll stay at the kind of qualitative level for now, but then I'll get into it more generally. But right, what's needed is really to show that for every real instance of classical behavior, there is a quantum mechanical description that approximately instantiates the physically salient features of the classical description. And of course, cashing that out in mathematics is going to require saying, well, what are the physically salient features, right? What do we mean by instantiation, and so on, right? And so this functional notion of reduction, I think, is really kind of neatly summarized in a quote by David Wallace, right? And he writes that, right, this instantiation relation, I claim, is the right way of understanding the relationship between different scientific theories, the sense in which one theory may be said to, quote, reduce to another. Crucially, this reduction on the instantiation model is a local affair. It is not that one theory is a limiting case of another per se, but that in a particular situation, the, quote, reducing theory instantiates the, quote, reduced one. And Butterfield and Gomez just recently have also drawn a connection between functionalism and reduction, right, and kind of advocate a functional approach to reduction. Right, and so it's important to note that, right, so there are elements of reduction 1 and reduction 2, right, so Nagel-Schaffner and limit-based reduction, right, that are really do capture what tends to happen in many reductions, but the ways in which those approaches are right, they kind of, the properties of reduction that they emphasize tend to be, they put them at the center, and I'd rather that argue that they're in some sense play more of a supporting role, right? So right, so like bridge laws, right, functional instantiation relations establish a sort of translation between the descriptions of the system, but there's no requirement that those instantiation relations be one-to-one across all contexts. And the context in which instantiation occurs, right, may be but need not be characterized by certain limits, right? So maybe you confine yourself to a certain region of the state space or a certain region of the parameter space of the Hamiltonian, right? So those sorts of restrictions can be characterized in terms of limits, but it's not like a sine qua non of reduction that limits be involved. Okay, so functional reduction, I've argued, although I didn't use the term functional reduction, but I think it's more or less implicit. Right, so functional reduction is a basic local relationship between two models of the same physical system, right? So we for any system that's well described by the high-level theory, right? So by some model of the high-level theory, there needs to be some model of the low-level theory that approximately instantiates the physically salient features of the high-level model, right? And what's kind of less often recognized is that reduction is often an empirical relationship, and for that reason, it's kind of subject to a lot of the vagaries of confirmation theory and induction. Right, so it's an empirical relationship depending on the scope of applicability of the reduced theory or model. Right, so functional reduction requires, right, the low-level description to approximately instantiate the high-level description in those cases where the high-level description is empirically successful. Right, and so that some characterization of the domain in which the high-level description is empirically adequate is essential for reduction, right? Because we don't want to require that the low-level theory capture features of the high-level theory that actually aren't realistic. Right? And so in that sense, reduction is really kind of a three-place relationship, right? Because there is that element of confirmation theory and these kind of vagaries associated with induction that enter into reduction. Okay, so functional reduction, right, straightforwardly kind of gets around the worries about multiple realization and singular limits, I would argue. Right, so the instantiation relationships can be context dependent, right? There's no need to identify, right, properties of the high-level description with just a single property of the low-level description across all contexts, right? Different features of low-level theory can instantiate the same high-level feature across different contexts. And singular limits in the functionalist approach, so as I'll argue in the case of the quantum classical correspondence, right, there's no reason to think that instantiation or a functional, showing that some quantum feature approximately instantiates classical regularities, right? There's no reason to think that the particular limits that, say, Batterman focuses on are necessary for that, right? So the fact that they're non-singular is kind of neither here nor there, right? As concerns, right, the particular functional notion of reduction. Okay, So skepticism about functional reductionism, right? So assume that we have adopt a kind of reductionism on the basis of a functional notion of reduction, right? So what are the grounds for anti-reductionism relative to this particular notion of reduction? And I would argue that there's still plenty of room to be anti-reductionist, because a lot of the arguments, right, for particular reductions, right, they have significant gaps in them. They have significant holes. And so I want to kind of distinguish between two kinds of gaps. One I call an inductive gap and another a deductive gap. And I'll explain what these are. Right. So claims about reduction, so first inductive gaps, right? So claims about reduction, as I've said, are ultimately claims about the empirical scope of our theories, right? That the empirical scope of the low-level theory strictly encompasses the empirical scope of the high-level theory. And so I would argue that the kind of a worry voiced by Cartwright is really more salient than either the multiple realization or singular limits approach, right? So she argues, right, we only test our theories in carefully controlled contexts where the conditions are set up just so as to produce certain phenomena. And so she thinks it's too bold an inductive step to suppose that, right, the laws that the regularities that we see holding inside these kind of manicured laboratory contexts, right, extend outside of those contexts, right? So quantum mechanics is tested only in the lab. So why assume that it applies to baseballs or the orbits of planets, right? She thinks that's quite a radical sort of step. Okay. And yeah, so as I've said, so because functional reduction is partly empirical, it's subject to the vagaries of inductive inference. And so, for example, right, even in a case that's seemingly unproblematic, like the reduction between Newtonian mechanics and special relativity, right? So we think that all Newtonian systems are really kind of better described by special relativity, right? But there's no logical contradiction in supposing that some body moving at speeds close to the speed of light is actually better described by Newtonian mechanics than special relativity, right? It's just that we assume that special relativity is more universal, and every one of our observations confirms that fact, right? But it could be like kind of a black swan, where the next system we look, is moving really fast and it's better described by Newtonian mechanics, right? So it's not a plausible scenario, but it's just important to highlight the fact that it's inductive inference, right, that leads us to believe that such systems don't exist, and that reduction holds, right? That all Newtonian systems are also special relativistic systems, right? There's an inductive inference embedded in that. And again, it's not to say that we should believe that. It's just to highlight the role of inductive inference in claims about reduction. Right, and so given these inductive gaps, the best we could hope for in reduction is really to take certain paradigmatic systems and show how reductions occur in specific contexts, right, between the models of those systems. So I don't think there's any conclusive proof that can be given that all contexts in which one theory applies are also contexts in which another applies. The best we can do is spot check across different paradigm systems. Okay, so deductive gaps, right? So putting aside the inductive worry, right? So even for particular systems, right? So focus on just a single context, right? Where we're relating two models of a single concrete physical system, right? The computations needed to show that an underlying model, right, approximately instantiates the physically salient features of a high-level model, right, may be prohibitively difficult in practice, right, and require the use of non-rigorous plausibility arguments, right? So for very complex systems, right, performing a deduction that shows that some function of the low-level state, the microstate, right, approximately satisfies the laws of the high-level theory, right? As a practical matter, that may just be impossible, right? Reduction requires that it be true, but to actually show that it's true is prohibitively difficult, right? Right. So for example, in the case of open quantum systems, right, in principle, right, a functional reduction requires that it be possible to deduce, right, from the underlying unitary dynamics of the system and environment that the partial trace of the global system environment state approximately satisfies some particular master equation, right? But when you think about what the actual underlying unitary description of the system and environment is, it's extremely complicated, and it's in some sense not even worth writing down, because in some sense it's a whole universe. Right. So really, I think in these sorts of contexts, right, rather than rigorous deductions, we have to settle for plausibility arguments. And the reliance on rigorous deduction rather than on plausibility arguments rather than rigorous deduction also opens the functional reductionist up to kind of critique from the anti-reductionist. And it's those particular weaknesses that I think are the legitimate grounds for reductive skepticism. Okay, so just to summarize the first part, right? So the main grounds for skepticism about functional reductionism, right, come not from any knockdown argument like multiple realizability or singular limits, right, but from skepticism about particular reductions, right? So in particular, right, inductive skepticism about, right, the empirical scope, right? So you might have shown that, you know, for some particular set of systems, right, those systems are at least as well described by the low-level theory as they are by the high-level theory, right? But that doesn't provide any conclusive proof that some other system that's well described by the high-level theory will also be at least as well described by the low-level theory. And then there's also, right, the deductive skepticism, which is skepticism about the plausibility arguments used in proofs of functional reduction, right? Proofs that some, right, low-level feature approximately instantiates the physically salient high-level regularities. Right, so these are I think the main routes open to the anti-reductionists, and so there's a question, right? How seriously should we take these concerns? And I think that this question can really only be answered on a case-by-case basis, right? You need to really look at the arguments that have been given for the particular reduction in question. Yeah. Okay. So having said that, I want to now focus on one particular case, right, which is a particularly important case, right? And so really kind of probing the gaps, but also kind of the strengths of the functional reduction of classical to quantum mechanics, and to emphasize the role of quantum unravelings, which I think have really not been, right, acknowledged in the philosophy of physics literature. Okay, so when we talk about classical behavior, right, there are a few things that can often be meant, right? One is just determinate outcomes. Another is satisfying classical equations of motion, right? Another, you know, and one can also, it varies depending on which type of classical equation of motion. Is it a stochastic classical equation? Is it a deterministic classical equation? Is it an equation for a probability distribution over this phase space? Right. So just saying, you know, the classical limit or, you know, classical domain is not really, it's ambiguous until one specifies which kind of particular features of classicality one's looking to recover. But I would say, right, that all of these things really should be recovered by quantum mechanics, right? Insofar as they're, right, that they represent, you know, they provide some approximate description of real systems. All right, so one might think, well, okay, if we're talking about, you know, how quantum mechanics can describe realistic classical systems, right? Well, there's no getting around the measurement problem, right? Because if you try to kind of, you know, try to apply the sort of textbook collapse theory, right, to a baseball, right, you don't really get anywhere, because, right, if you measure the position of the moon, right, according to the textbook interpretation, right, you get, first of all, it doesn't even tell you exactly when collapses occur or how you set up a particular measurement or particular operator, or, you know, and if you measure position, right, you collapse onto an exact eigenstate of position, right, which is problematic in itself because it contains arbitrarily high momenta and spreads infinitely quickly. Right, so it would seem that if you want to describe something that's kind of continuously being measured, like, you know, a baseball or the moon, right, right, you need to do better than the kind of textbook account of measurement and of collapse. And so you might think, well, okay, you need a solution to the measurement problem. And what I argue here is that although in principle we still want a solution to the measurement problem, right, we can kind of, you know, details about the collapse mechanism because of decoherence theory, right, largely decouple from the kind of quantitative explanation of classical behavior. That essentially, right, we can tell more or less the same story across every interpretation, right? And then just kind of shoehorn in the collapse mechanism at the end, assuming that the collapse mechanisms are decoherence compatible. That is to say that, right, so decoherence theory, right, assuming so it defines a unique branching structure up to coarse graining, and right, and assuming that any realist interpretation basically serves to just select one of those branches according to the Born rule. Right, so that's what I mean by decoherence compatible, is that the collapses are always onto decoherence preferred states, and so essentially, right, so what this diagram here shows is just how, right, the kind of branching structure defined by the unitary evolution, right, how it's exploited in different realist interpretations, right? Now, right, there's some doubts as to whether, right, you get exactly the same, right? So given the branching structure defined by the unitary evolution, right, is it always true that the kind of Bohmian hidden variable actually picks out those branches, on decoherence, that it doesn't choose some other state that is not one of the branches, and similarly for GRW, right? But I think the decoherence is empirically quite successful. I think it's well confirmed across a wide variety of contexts, and I think it's generally a virtue of a realist account of collapse that it basically agrees with the sort of predictions of decoherence theory, agrees with the branching structure. Right. So one important thing about decoherence theory is that it essentially gives us a kind of middle ground, right? We don't need to fully solve the measurement problem, right, in order to talk about macroscopic objects, things like baseballs or the center of mass of the moon or something like that, right? That we can basically avoid kind of committing to any particular collapse mechanism, but still give a very precise quantitative account of macroscopic classical behavior, of deterministic classical trajectories, without committing to any particular collapse mechanism. Right. Okay. Right, and so the idea essentially is, right, so assuming that we've got some well-defined branch structure via decoherence, right, say described in the decoherent histories framework, right, then what that branching structure does is essentially what we can do. Sorry, I'll go back for a sec. Right, so the way we can kind of get rid of or abstract away from particular collapse mechanisms is just assume that by some mechanism at every branching of the quantum state, right, some particular branch is chosen, or is selected in accordance with the Born rule, but we don't know exactly how, right? We just know that there's a well-defined branching structure, and that, and that the reality we experience somehow chooses one of those branches at each branching point. And so we just kind of table the question of what the precise mechanism is whereby one of those branches is chosen. But it turns out that, right, that's precise enough. Right, so it does way better than a textbook account of quantum measurement and of collapse, and it enables us to give a precise quantum description of determinate stochastic trajectories, which ultimately, if the noise is small enough, will give rise to classical trajectories. Okay. So right, so really we have so classical mechanics or classical trajectories are often, so they're recovered as branch relative dynamics, right? So they're recovered by a certain branch relative or branch specific stochastic dynamics, right? So the branching of the quantum state and some kind of black box collapse mechanism that's compatible with the decoherence, with the branching structure, right, induces a stochastic evolution for the expectation values of position and momentum in classical phase space, right? So imagine that, so this diagram is, right, so this is just, imagine that this is a classical phase space, and that basically we have different branches, which is, so these are basically the phase space trajectories, right? So the evolutions of the position and momentum expectation values with respect to the different branches, right? And then the dotted blue line is the Newtonian trajectory, all right? And then the red line is the quote actual trajectory, right, taken by the system. And so, right, so there's an open systems form of Ehrenfest's theorem, right, that entails that as long as the spreading of the kind of ensemble wave packet, that is the wave packet across branches, is not too rapid, right, then all of these branch relative trajectories will provide a good approximation to the Newtonian trajectory. So it will take the form of a Newtonian trajectory plus some small noise term, which can be neglected. Okay, so that's kind of the kind of conceptual overview. Now, when it comes to so the reason I think
hold on, Josh, do you mind going back one?
Yeah, sure.
But the important point is that there's antecedents for Ehrenfest theorem, right? So it won't hold in general.
So Ehrenfest theorem holds in general, but the relevant result is for narrow. So if you look at the reduced density matrix of the system, you want it to be narrowly peaked along the diagonal.
Yeah.
And then that will basically let you take the expectation value of the force and turn that into approximately a force as a function of the expectation value of position and momentum.
But I mean, I guess it depends what you mean by Ehrenfest theorem. But like, I thought the idea is that in some systems you can get the expectation value wandering away from the classical trajectory.
Yeah.
You don't need.
Yeah. Go ahead. Sorry.
So you say, I guess you don't need the classical trajectory, the expectation value to follow the classical trajectory for this to hold, because I thought there are quite clear examples of that, at least that condition, which I'd informally call an Ehrenfest theorem to fail, although it's not. I think it's not identical with it.
Yeah. So so in the case of a classical harmonic oscillator, so I think that's kind of the unique case in which the expectation value exactly satisfies the classical equations of motion.
Yeah.
And in all other cases, right, the expectation value cannot be expected to satisfy the classical equation of motion. However, if the reduced density matrix, if its width along the diagonal, so if it's ensemble width, right, so if it's basically a narrowly peaked wave packet, then what you can do is you can show that expectation value approximately satisfies the classical equation of motion.
I will have to, maybe this is a longer thing. I thought there were at least some systems in which it doesn't even approximately, it can vary wildly away from it.
Yeah, I mean, so there are some, I mean, if those systems are not narrowly peaked wave packets.
Oh,
then,
okay.
So you need to impose a constraint on the state, and if you don't impose that constraint,
then
because
like even if you just quantize a simple cosmological model, it can obviously wander wildly away from the classical trajectory because you can get these weird singularity behaviors, right? Or not.
Yeah.
But you're okay, right? So the point is that it's really about the ratio of how wide the packet is to how much you allow it to, how close you expect it to be.
Yeah, exactly, right.
So long as it's peaked enough, it'll be close enough.
Exactly.
Okay. Great.
Yeah, and so and you also want the rate of spreading to be slow. So if you want to recover classicality over long time scales, you need the rate of spreading of that wave packet to be slow.
But the question is whether this is true for generic states or specific states, and it's generally just it's states that are peaked enough it will be true for.
Right, it's only true for specific states.
Okay, great. Thank you
generally,
very much.
Except in the harmonic oscillator.
Thanks. I'll try and stop interrupting so much. But thanks.
No, it's fine. No, I welcome it. Yeah, and so basically
just a second.
Yeah.
I mean, this is a question of asymptotic. So you speaking about narrow wave packets. That's another way of saying that in some appropriate regime where Planck's constant is small compared to other things, the trajectory, the expectation value will be close to classical trajectory, provided you don't wait too long. And the length of time you have to wait for it to fail is longer and longer as Planck's constant, suitably normalized, gets smaller. So, you know, this is, you mentioned earlier on, this non-commuting of the two limits. Never mind that. I mean, for any particular time, however long it is, if you have a wave packet narrow enough, then if you avoid singularities and whatever, then Ehrenfest theorem can be applied in the naive way, and you essentially will follow the trajectory. I mean, the spreading you mentioned is particularly dangerous if you have chaos, of course, classical chaos, and the spreading is dangerous. But even then, if you have a fixed time, and you can always make the system semi-classical enough for it to follow. I mean, I'm agreeing with you.
I think I agree with everything you've said.
I'm responding to Karim's point. That's all. I mean, I don't delay you.
Yeah, but I would say that, like, I mean, unless you include the environment, right, you don't get this branching effect.
Well, that's another thing which
Yeah.
we want to talk about in the discussion. I mean, that's
Yeah.
very, very important. Yeah.
Yeah. So I think I mean, without the environment, essentially what you get is just a coherent wave packet spreading at the kind of width of these branches, but the branches aren't there. Like, so it's just a coherent wave packet spreading. But with the environment, what you get is that as the wave packet spreads, you get a branching into
sure.
And oh yeah, this is just a point I kind of want to clarify just for the whole audience, I guess. But yeah, that wasn't kind of specifically in response to what you're saying, but yeah, just yeah. So basically, relative to a particular branch, right? The dynamics is still approximately classical. Because all of the branch relative trajectories are bundled around the Newtonian trajectory, but there is a small stochastic component, right, surrounding the deterministic component, and you don't get that small stochastic component without the environment.
Yeah, so it's a technical matter, a case-by-case matter, to ask which kind of to ask when this environment effect comes in, and in many cases of carefully designed experiments, you don't need to consider it. But in principle, it will, for long enough times, sometimes that's quite a short time, that the environment is important. So it's a matter to be understood case by case, whether you need to include the environment in every case.
Right. Yeah. And so I guess the claim would be that for macroscopic systems, yes, right, that we typically see exhibiting classical behavior, that basically in all of those cases you would basically need that. But that, yeah, and isolated laboratory systems where we don't generally expect to find Newtonian trajectories, you know, they're classical in different senses that you've kind of elucidated, I think. You know, but they're not classical in a kind of narrowed sense that the determinate trajectories following approximately Newtonian trajectories.
Okay, good.
Yeah.
Good.
I suggest we let Josh finish his talk, and I'll try and refrain from doing more interruptions myself.
And so the role for quantum unravelings, I would say, is that it permits us to model the kind of deterministic stochastic, the determinate stochastic branch relative pure state and phase space dynamics precisely, right? So relative, so I'll just go back, relative to any particular branch, right? The state of the system itself is actually a pure state. It's not a reduced state, right? It's only, right, so you only need reduced density matrix if you're talking across branches, right? But if you're focusing on one particular branch, then between the system and environment, the state's approximately a product state. And so you can talk about a stochastic pure state evolution of the system relative to a branch. Right, so the formalism of quantum unravelings, what that permits us to do is to model the branch relative stochastic pure state dynamics, right, and also the kind of corresponding phase space dynamics that you get from taking expectation values, right? It enables us to model that stochastic branch relative dynamics precisely, and for that reason, it plays, you know, it's an important step in the functional reduction of classical to quantum mechanics, right? So the kind of general steps in the functional reduction are as follows, right? So assume that we have some physical system, say a baseball or the moon, or some, you know, just any sort of system that follows a Newtonian trajectory. Right. So the high level model, right, the classical model will be some Hamiltonian model of the system. The low level model will be kind of unitary dynamics of the system and its environment, because the environment will matter, especially if it's macroscopic. And so basically the chain of deductions, right, goes from the unitary dynamics of the global system environment, right, tracing over the environment to get a master equation for the reduced density matrix of the system. And this will generally require some restrictions on the state of the environment. And then given the master equation for the reduced density matrix, right, right, so if you assume, right, collapse, every time you have a branching, you have a collapse onto some particular branch, right, according to the Born rule, but being agnostic about the specific mechanism, right, then the master equation can be converted into a stochastic pure state evolution for the pointer state of the system, right? So we can just now imagine, right, given the branching structure, that actually defines a stochastic evolution in the system's Hilbert space of a pointer state. So the pointer state changes over time stochastically. And so given the stochastic pure state evolution for pointer states in S, right, taking expectation values of position and momentum relative to that kind of localized pointer state, right, induces a stochastic dynamics on classical phase space. Right? And if the noise associated with that stochastic classical phase space dynamics is small, we get deterministic dynamics on classical phase space. And I would say that it's that constitutes the kind of functional reduction of classical to quantum mechanics. It's those expectation values relative to the kind of branch relative pure state, right? That ultimately instantiate, right, a classical phase space point. Right. So just to give a little bit of a flavor of how a quantum unraveling works. So we start from the point where we have, right, some right, master equation for the central system, right, for the reduced density matrix, and some Lindblad equation, and from that can be extracted, right? Or rather, right, so we can associate with that reduced density matrix evolution a pure state evolution on the Hilbert space of the system, right? That's stochastic, and the first term is basically just a drift term, and the second term, right, it includes some random noise process, right, associated with the variable psi, and u and v are just functions of psi. So basically, such a stochastic pure state evolution on the system's Hilbert space is called a quantum unraveling of the master equation, right? If the ensemble average, right, over particular realizations of the stochastic evolution, right, returns the reduced density matrix evolution. Okay, so basically, if by averaging, right, so basically averaging over these realizations, but weighting those by the probability of each noise, of each particular realization of the noise process, if we average over those stochastic trajectories, we recover the reduced density matrix evolution. Okay, and right, so it turns out there's actually an infinite number of this. So the unraveling associated with a given reduced density matrix evolution is non-unique. So there's an infinite number of distinct stochastic pure state evolutions that can be associated with a given density matrix master equation. But there is one possible unraveling, right? So one such example would be the stochastic Schrodinger equation given here. And so generally, quantum unravelings are useful calculational tools for numerical computation of density matrix evolution. So they don't necessarily have a clear physical significance in terms of some pointer state. Right, they're just computational techniques for computing the reduced density matrix evolution. However, there are special quantum unravelings that do have physical significance, where the stochastic, right, pure state evolution can be interpreted as the evolution of the pointer state relative to a particular branch of the quantum state. Right, and so this is sometimes called right, the nonlinear pointer state evolution. Right, and it's associated with a special unraveling of the master equation. So if you're given some underlying model, like the model for quantum Brownian motion, right, there's a special quantum unraveling associated with the master equation for quantum Brownian motion that describes the stochastic evolution of a pointer state for the system. Right, and so if we take expectation values of position and momentum, right, in the central system's Hilbert space, right, with respect to this kind of stochastically evolving pure state, then we recover, right, approximately classical equations of motion, but with some additional noise terms. So there's dWs in these W's in here, right, are these kind of Brownian motion terms, and so that they're stochastic components, but. Right, in cases, right, and so these coefficients of the stochastic components have to do with the second moments of position and momentum with respect to the pure state. So that this what this Vx and Vp and Cxp are. Right, and if those second moments are small enough, and so if the variance is small enough, if the wave packet is narrow enough in both position and momentum, and also with respect to this kind of covariance, then we can ignore the noise terms, right? They're small, and so we recover deterministic classical equations. And so this is closely related. So right, so these quantum trajectory unravelings are actually specific examples of decoherent history. So each realization of the noise term in a quantum unraveling is actually a specific branch of the quantum state in a decoherent history's decomposition. Right, so we can, in decoherent histories, right, we can decompose the state in terms of these history operators, which are basically, alternating sequences of projectors and unitary evolution. And once we determine what that branch structure is according to decoherence, right, there's a specific quantum unraveling, and the realizations of the stochastic term and the noise process correspond to different consistent histories or decoherent histories. And specifically, right, so often, right, in reality, we don't want the histories just to be merely to be consistent, but to be partial trace consistent in the sense that they're orthogonal specifically with respect to the environment. And so this is what Finkelstein called partial trace consistent. Right? And so with respect to different realizations of the noise term in the quantum unraveling, right, we expect the associated branch operators to be, or the associated branch states to be orthogonal with respect to the environment. Right, and so just coming back to the functional reduction of classical mechanics to quantum mechanics, right, the quantum mechanical quantities, again, that instantiate classical behavior are these kind of branch relative expectations of position and momentum, right? So with respect to particular realization of the quantum unraveling. And so, right, so we can write it out in terms of the kind of stochastic state evolution, right, in equation 11, but we can be even more explicit and go down even further to a more fundamental quantum level of description, where we express these expectation values in terms of the fundamental branch states defined by decoherence, right? And so the functional reduction, right, is saying that, so these quantities, right, so these expectation values, which are functions of the branch states, right, these are the things that approximately instantiate classical behavior, right? So anytime we look at a baseball, we should think that what's really going on is what's given in equation 12. So what I'm really looking at when I look at the trajectory of a baseball, right, is actually some branch relative expectation value of position and momentum. Okay. So there are, right, so there's some so there's some pretty significant, right, so this is the general narrative. So I've just given a kind of an outline of the structure of a kind of decoherence-based approach to functional reduction of classical to quantum mechanics. But there are significant deductive gaps in this kind of chain of reasoning, right? It's more an outline of a proof than a proof, in a sense. Right, and so one problem is, right, the phenomenological nature of open system master equations, right? There's no rigorous derivation typically when we're describing some open quantum system of the master equation from some exact microscopic model of the system environment dynamics, right? Even though functional reduction, right, implies or requires that there be some feature within that microscopic dynamics that approximately instantiates those master equations, right? But so it requires that it be true, but for various reasons, it's basically impossible to prove rigorously. Right. Then there's also worries about the non-uniqueness of the branch structure. So everything above is assumed that there's some unique branch structure that's used to define the branch relative dynamics. But typically in the consistent histories literature, right, they just impose consistency, which is just a requirement of orthogonality of the branch states. And it turns out that radically underdetermines the branch structure. There are many incompatible branch structures that are consistent with the same unitary evolution that satisfy that requirement. So more needs to be said about how the branch structure is defined, right? So for example, you can add additional conditions like this partial trace consistency, right? You can require that the branch states be approximate product states between the system and environment. But then there's a question of, well, how do you justify the system and environment split? Because, right, so there's an asymmetry between system and environment insofar as the system leaves its imprint on the environment, but typically not the reverse. So it's not a completely arbitrary distinction between system and environment. And so, but at the same time, what constitutes a system is ephemeral, right? So, right, so what baseball is just a collection of atoms, and if it disintegrates, right, it's no longer really the sort of system that would necessarily, that collection of atoms is no longer the sort of system that would leave its imprint of its trajectory on its environment, right? So the system environment splits themselves are emergent and ephemeral, and there's a question about what dynamical features of the evolution justify that system environment split. Then of course there's the measurement problem. So if you're realist, right, there should be some clear physical story about how what causes one branch, assuming that we've got a well-defined branch structure, how a branch is picked out according to the Born rule, and right, for the purposes of making quantitative predictions, it turns out we don't need that collapse mechanism, but for the purposes of telling a physical story, we do, I think. And so that's still an important part of the problem, even though it can be sort of decoupled from the rest of the problem. And yeah, so given these gaps, right, how skeptical should we be of the claim that all classical systems are quantum? And I would say that in spite of these gaps, we shouldn't be very skeptical. So open system master equations, right? So you know, I think it's plausible, if not rigorously proven, that open system master equations can be rooted in a sort of global unitary dynamics of the system and environment, and there are various universality arguments that show that those master equations are largely insensitive to underlying details of the of the microdynamics. So the universality of master equations, right, lends a certain additional plausibility to that claim. The non-uniqueness of the branch structure. So I think that that's a problem that needs more work. But right, so in some sense, if we're allowed to assume a system environment split, then the decoherence theory through the use of pointer states, and Zurich's predictability sieve, if we're allowed to assume the system environment split, provides a well-defined branch structure, but it's just a question of how we derive that system environment split, I think. So the successes of decoherence theory, I think, offer plenty of reason to be optimistic, but there's still, there's still gaps in the argument. And quantum measurement, right? So by what mechanism is a branch selected as the outcome, right? So assuming, as I've said, assuming a collapse is always onto a decoherence preferred basis, recovery of classical behavior is largely decoupled from the detailed dynamics of the collapse mechanism. And it's reasonable to extrapolate, I think, that even if we're not sure what the correct collapse mechanism is, that there is some story to be told, right? That there is some physical picture to be had. That's true. Okay. Now those are the deductive gaps, inductive gaps. So right, so even if one can show, right, that certain features of quantum mechanics, right, instantiate classical regularities in one context, it doesn't necessarily mean that this sort of story can be told for every instance of classical behavior. I don't know, but I guess my sort of intuition about that, for what it's worth, is that that's kind of just making it, going out of your way to be difficult in a sense. If there's a mechanism that applies across many kind of spot checked cases, that gives a kind of plausible story in many individual cases, then the more we confirm it, the less reason we have to be skeptical that it extends to unobserved cases. And I think that there is lots of numerical and empirical evidence to support at least specific results from decoherence theory. So I would just like to conclude first with a little quote from Bhattacharya, Habib, and Jacobs in an article on quantum unravelings, and then to summarize afterwards. So they write, note that the task of explaining the quantum to classical transition is essentially a practical question. It is a question of explaining why real systems, such as nonlinear pendulums, baseballs, and other systems which can be built, observed in the laboratory, obey classical mechanics, at least to within any experimental error. It is not a question of obtaining classical mechanics precisely as a formal limit of quantum mechanics. In fact, due to the absence of chaos in closed quantum systems and the non-commutativity of the twin limits h bar goes to 0 and t goes to infinity, efforts to extract classical chaos as a formal limit have been less than successful. If one describes macroscopic objects sufficiently realistically using quantum mechanics, then it should be possible to predict the often chaotic trajectories of classical dynamics. In order to do this, it's important to realize that all real classical systems are subject to interaction with their environment. Right, so the argument here is that, right, because of their unrealistic assumptions, closed system approaches based on formal limits, including the singular limits that Batterman mentions, really are largely tangential, right, to functional reduction, right? So that they don't really come into it in any essential way. Okay, so then just to summarize, right, so reduction in general, so the form of reduction most relevant to reduction in physics, I argue, is functionalist, insofar as reduction is a claim that all theory A systems are also theory B systems, but not necessarily the reverse. Right, traditional anti-reductionist arguments for multiple realization and singular limits are really just, in some sense, addressing straw man forms of reductionism. And the strongest basis for skepticism about the possibility of functional reduction rests on, right, a careful analysis of detailed arguments for reduction, in particular on the deductive and inductive gaps that exist in those arguments. In the particular case of quantum classical relations, right? I've argued that decoherence theory provides a framework for functional reduction, and that there are significant deductive gaps in that account. I've also emphasized that quantum unravelings provide an important step, right? So they're an important piece of that picture, of that story that's often neglected in the philosophy of physics literature. But they really give us essentially the classical dynamics, right? They tell us what the branch relative stochastic dynamics of the system is, and that's what most directly kind of instantiates the classical dynamics. And closed system approaches based on formal h bar goes to zero limit, right? They're unrealistic in their physical assumptions, and for that reason, right, results that seem problematic are actually largely tangential to questions about functional reduction. Thanks.
Good.
Fantastic, thanks, Josh. So what I'd suggest is that first and foremost, we use the chat for the questions, and if you'd like to ask a question, could you put a Q or write question in the chat? But if everyone can put them in, and but the students can, I'll put the students first, and if I misrecognize you as a student, then let me know. But yeah, please, if any of the graduate students or undergraduate students have questions, do put them in now, and we'll give you kind of priority. And
Me is Michael Berry.
yeah. No students with questions, so certainly if you don't have a question now, you can ask a question later.
Yeah.
Lucy, go ahead. So Michael, just to double check, you need to go at 10 to.
I will need to leave, so.
Why don't you go first then, and I'll put the students out after you. That's totally fine.
I would like to. Okay, Joshua, thank you very much for this. It was all good sense. I agree pretty much with all of it. And I particularly like the way you emphasized a lot of the subtleties which are involved. But I do want to make a couple of points. And one is essentially adding to what you said, which is this, that as the systems get larger and larger, the time scale on which decoherence happens gets smaller incredibly rapidly. I mean, there's one that, especially if the classical system that you're aiming to limit to, it has chaotic motion. And there's this example, I don't know if you know it, of the chaotic tumbling of Saturn's satellite Hyperion.
Sure, yeah.
Now that's been, it was observed, and it has a chaos doubling period, exponential, etc., of about a month. Now, quantum mechanically, if you think of that rotating object as an isolated quantum rotator, then you can predict using wave packet spreading arguments that the quantum spreading time when the chaos would be suppressed would be, about 20 or 30 years. And that's nonsense. You don't observe Hyperion for 20 or 30 years and see it not being chaotic anymore. And the reason, exactly what you said, is because you've got an environment, and even one photon from the sun hitting it, whose re-emission you see Hyperion by, would cause decoherence in about 10 to the minus 50 of a second.
Right.
So it's an incredibly important thing as systems get larger. So that's one feature I learned from Wojciech Zurek, and I did some calculations myself, that particular one. But there's something else which is the following. What you've discussed, subtle and difficult though it is essentially a reassurance exercise. You do know that there's a sense in which quantum systems, which not the spin half, but most of them, will in fact behave classically, and it's just difficult to show it, but you've described how it's an important feature. And underlying it is a suppression of interference. Right. Now, this really goes back to Thomas Young in 1801, because people bitterly criticize him, say, well, look, if you think of light is a wave and you see interference, why don't we see interference all the time? And he said, and it's really decoherence, well, there are effects we can't control, there are imperfections, multiple frequencies and whatever. And essentially that's all the blurring of interference by external influences that you don't have control of. The light's not monochromatic or whatever. It's essentially the average of cos squared is a half. I mean, that's the heart of it.
Okay.
It misses the feature I mentioned earlier, that it happens very quickly as the system gets bigger. But that's however, all of this is only one aspect of classicality. You are right that isolated systems miss the effect of the environment. Nevertheless, the quantum mechanics of isolated systems is important in the sense that in cases where you can reduce interference and environment more and more and more and look for longer and longer times, different universal features emerge precisely because the limit is singular. And this is a whole class of phenomena being intensively studied. So, for example, if you look at the high excited states, they get closer and closer together as the systems get more complicated, or as Planck's constant gets smaller relatively, system gets heavier. We look at the high excited states, which of course classically they don't exist as discrete states. Classically, you have a continuum of energies, and you ask, what are the statistics of the distribution of these enormous numbers of high excited states? Universal features emerge which depend on features of the classical dynamics, but it's not a classical limit itself. So, for example, the periodic orbits of the underlying classical system determine this class of phenomena. Then you ask, what are the morphology of wave functions in chaotic systems as you get more and more classical? There are detailed statistics observed in experiments and important for explaining certain phenomena. So there's this whole class of borderland phenomena which arise precisely because the limit is singular. If the limit weren't singular, for example, special relativity going to Newtonian mechanics, V on C becoming small, you don't have these borderland, but almost everywhere else in physics you do. So, for example, in fluid mechanics, as you let the viscosity get smaller and smaller, you would think to the motion of a frictionless fluid, Euler's motion, you can solve exactly. Well, that's not what you observe. You observe turbulence. Turbulence is an emergent phenomena as the viscosity gets smaller, because although the dissipation it gets weaker and weaker and weaker, it gets distributed on a more and more complicated fractal set. And this dramatic phenomenon of turbulence, which occurs in a huge number of contexts, is a borderland phenomenon. It's a high Reynolds number phenomenon emerging, but not in the limit of infinite Reynolds number. You know, critical phenomena in thermodynamics, statistical mechanics, where the limit isn't thermodynamics as you expect for large N. This is Anderson, more is different, you know, but it's a class of phenomena that emerge, but which are not the limiting phenomena, but they occur on the way to the limit when the parameter is either large or very small. So this concentrating on how does quantum reduce to classical is part of the story, and it's very important, but it misses these borderland phenomena, which is a lot of the physics of the last half century has been to understand these. And in mathematics is very difficult, and but we slowly make progress. So that's my comment. It's not a criticism. It's just because what you wanted to explain, you described very well. But there's more to it. That was my point.
Yeah, no, thanks. Yeah, no, and I mean, the point's very well taken.